Simulating and downloading a PIC circuit to Xilinx FPGA boards using TINACloud. In this video, first we'll demonstrate how to simulate and synthesize a circuit displaying prime numbers using a PIC MCU VHDL code. In the end, we'll download the circuit's configuration file to the BASYS3 FPGA board. Okay, now open the PIC X6 prime number generator circuit from the TINA Examples FPGA folder. This circuit calculates prime numbers between 1 and 9,999 and shows them on a 4-digit 7-segment display. The display has 12 pins. The MCU port RA lines from RA0 to RA3 are connected to the display digit selector pins. They are used to turn each digit on and off. If we double-click the display, the catalog property shows us that our display is of the common cathode type. This means that all the cathodes of the 7 segments within a digit are connected directly together. To turn a digit on, the appropriate selector pin should be asserted at a low level. Port B drives the 8 LEDs, the 7 segments, and the decimal point. These LED connections are the shared segment pins of the digits, but only one digit is active at a time. In this circuit, the PIC MCU model is written in VHDL. The VHDL code is the functional model of a PIC 16F84 8-bit microcontroller with initialized flash program memory. CLK1 provides the external 10 MHz clock. Okay, now let's look at the VHDL code. Double-click the MCU. In the Properties window, click the 3 dots, Details, at the end of the HDL code field. The top-level entity is RTL_PIC. In the Architecture section bound to the RTL_PIC entity, line 1828, we instantiate and connect the main components. These components are the PIC core, line 1830, the 1K times 14 bits flash_ROM, line 1890, and the PIC 16F_RAM file register, line 1898. From line 1941, the instantiation statements connect these declared components to signals in the architecture, 1941 to 2002, followed by auxiliary VHDL code to support reset and I/O updates. Okay, now let's take a look at the flash_ROM entity, line 63, where the prime number generator program was loaded. The case construction, line 76, describes the ROM functionality. The ROM content, line 78 and following of the program code, has been written in C, which we have already converted to this VHDL code. Close the dialogues. Okay, now let's look at the C code. The project was created and the program was developed with the free version of Microchip MPLAB IDE and their Microchip XC8 compiler. Start MPLAB. First, we define sim, indicating that we are running a simulation, line 3. If sim is defined, then other constants are created in lines 6 through 10. The XTAL FREQ is the processor frequency for the simulation. The other parameters are for handling the display. The code writes prime numbers between 1 and 9,999 with the help of a for loop starting from line 98. If a number is prime, we will generate the digits and display the number. Note that for checking primes, due to the limited memory of PIC 16F84, we use a very short C code, but for large numbers, this C code runs slowly. We have 8 bits to write a digit, port B, and 4 bits, port A, to select which one to display. One digit is displayed for a very short time in the millisecond domain. When a digit is displayed, the other digits are dark. This process is performed from line 107. Now let's go back to the schematic editor of TINACloud. Start the simulation by pressing the Dig button. You can see the prime numbers written on the display. Stop the simulation. If you want to follow the transitions of the digital nodes, you can switch to the Show Digital Node States option
in the Preferences dialog
under the View menu. In this case, the node levels will be displayed. However, the simulation could be slower. Now, let's make the main difference in the C code for the synthesis. Open the C source file in the MPLAB Editor and comment the sim definition out in line 3. Thus, we have defined new constants, like the processor speed in line 12, 100 MHz. This is the oscillator frequency of the BASYS3 FPGA board. After that, we can compile the project and convert the result, the executable binary, into VHDL. The code is placed in the flash ROM component of our VHDL PIC model. Now open the circuit PIC 16F84 prime number generator BASYS3 from the TINAexamples FPGA folder. We have FPGA pins connected to the ports of the PIC MCU. Port A is for anode selection, port B is for selecting segments. Now let's test our circuit in a real environment using the Digilent BASYS3 FPGA board. First, let's generate the source file for Xilinx Vivado. Click the TNM menu and select Export to FPGA Software. Then click Xilinx Vivado. Next, open and extract the PIC 16F84 prime number generator BASYS3 FPGA export.zip. Create a folder. We'll name our folder Designs. Then copy the 3 files, including the 2 .vhd and .xdc files, into this newly created folder. To produce downloadable content, first we create the Vivado project. Start Vivado. From the File menu, select Project, then click New. Click Next. Enter the project name, in our case, PIC 16F84 prime number generator BASYS3. Click Next. Click Next again, then click Add Files. From the Designs folder, select all the VHD files as source files, then click OK. Click Next. Click the plus sign to add the PIC 16F84 prime number generator BASYS3.xdc file as well. Click Next. To finish project configuration, select Boards in the Default Part dialog. You can now select the appropriate board. Select BASYS3. Click Next. Click Finish. Now Vivado is initializing our project. Click Generate Bitstream to produce configuration data for the FPGA. Then click OK in the Launch Runs dialog. Now connect BASYS3 via USB with the Vivado machine and turn the board on. As soon as the Bitstream Generation Successfully Completed message appears, select Open Hardware Manager, then click OK. Now you can see the prime numbers written on the display. For more information, visit our website, www.tinacloud.com. Visit our YouTube channel, www.youtube.com/user/Tina Design Suite.